Good morning, everyone. Welcome to our third talk of SIBGRAPI 2021. I am Afonso Paiva from Instituto Ciências Matemáticas da Computação of University of São Paulo, and I'm going to be the chair of this presentation. It's a great honor to meet to introduce our next invited speaker, Professor Cláudio Jung. Cláudio got his PhD in computer science at Universidade Federal Rio Grande do Sul in 2002. Now he is an associate professor of Institute of Informatics at Universidade Federal do Rio Grande do Sul. He was also a visiting professor at University of Pennsylvania. Last year, he was an invited speaker of IEEE School on Digital Processing of Visual Sign and Applications. Cláudio is a very active researcher. He has published more than 50 papers in important journals such as IEEE Transaction Image Processing, Pattern Recognition Letters, Signal Processing, Computer Graphics Forum, Visual Computer, Computer Graphics, and so on. Moreover, he is a co-author of a book about crowd simulation. His research interests comprise topics in image processing, computer vision, pattern recognition, and deep learning. Today, Cláudio will talk about beyond horizontal bounding box for object detection. Before we start, I would like to encourage the audience to submit your questions to Cláudio through our YouTube chat or through our Discord channel as well. He will answer all these questions at the end of the talk. Cláudio, I thank you in advance to accept this invitation. Now it's up to you.
So thank you, Afonso, for the nice introduction. I'm very happy to be an invited speaker at SIBGRAPI. Actually, my first SIBGRAPI was like 21 years ago in Gramado. It's a pity that we are online and we cannot meet there. But anyways, let's try to do the best. So today I'm going to talk a little bit about some research topics that I have been investigating in the past year, and they relate to object detection, and more precisely to the representation of the shape of the object in the context of object detection. As it's written in the title, we are going to show some alternatives that go beyond horizontal bounding boxes, which is the default representation in most object detectors. So I'm going to start providing a little bit of context. As probably most of you know, the problem of image classification basically consists of identifying the set of categories that are present in a given image. So in this example here, you should see a cat. Probably the first cat is very visible. There is a second cat here. There is a table, a chair, which is very hard to detect, and it seems to be a person here. So there is an arm and what seems to be part of a leg. So of course, the definition of the categories this definition is highly dependent on the annotation of the images. And the problem of object detection basically is an extension of image classification. So you also want to find the categories, but also all the instances of each category. So in the example below, you can see here the two cats, and the shape of the object is represented as a horizontal bounding box or just bounding box. You can see a chair, a table, and there are two boxes for a person. It's not clear if it's the same person or not. So this problem of object detection, it has a long history in computer vision. So probably the first very popular approach was in the late 90s, was the face detector by Viola and Jones, but it's a generic object detector. And since then, a lot has changed. In particular, in the past 10 to 5 years, the introduction of deep learning in the process of object detection has boosted the results, the accuracy, and several drawbacks that were present in earlier deep learning approaches are mostly mitigated now. So in the beginning, deep learning was introduced mostly in the classification part. So still the first approaches using deep learning were based on sliding windows at several scales. So it was like a lot of computational cost. And the learning, the deep network was applied at the classification stage at each candidate. Then the next generation of methods basically moved to sparse proposals. Instead of evaluating a dense set of windows, there is only a sparse set of proposals that are evaluated. And probably the current trend now is to devise methods that try to identify for each spatial location of the image if there is an object, if there is which category, and then try to regress some kind of shape information. In this example here, and as I said before, as in most object detectors, the shape is encoded by a horizontal bounding box. So this is one of the state-of-the-art object detectors based on efficient nets, and it's called efficient net. So what's the basic pipeline in a deep learning object detector? There is a backbone, which is responsible for feature extraction. There must be two heads in the network responsible for classification, for identifying the categories, and localization to provide some kind of information about the location and shape of the objects. And all these definitions and the choice of the backbone are highly dependent on the data set, which contains the set of categories, how the shape is encoded, the variability, and related to the data set, there is the important issue of data augmentation. There is the choice for the representation of the object. As I said, bounding box is basically the default representation in most methods. There are some alternatives, and that's exactly the main focus of my talk here. And highly related to the choice for the codification of the object shape, it's the choice for the regression loss, which is very important to adjust the output, the location output, based on the annotations. So all these modules, they can be used in a kind of plug and play manner. I mean, you can just replace a backbone, you can use a VGG or ResNet, DenseNet, EfficientNet, and usually you don't need to change a lot in the remaining of the process. But there is some coupling. For instance, depending on the representation shape for the object, you can use certain geometric primitives for data augmentation or not. So these steps modules in a neural network, they are kind of independent, but there is some coupling among them. So of course, I said before that a lot has evolved since the first object detectors, but still there are several challenges. The first challenge probably relates to the acquisition conditions. So depending on the scenario, you can have captures during the day, at night, you can have blurry images, you can have motion blur, you can have defocus blur, you can have highlights, you can have strong shadows. And depending on the variability of the data set, maybe your method can kind of overfit even to a given kind of camera. And if you change the camera, but visually the scene doesn't look that different, maybe the result is not going to be that good. Another problem, which is not going to be exactly the main focus of this talk, is how to allow the network to detect objects that can have a very strong variation in scale. So you can see the image on the left. You have several categories. I'm not sure about the exact annotations in the COCO dataset. So for those of you who are familiar with object detection, probably you have already played a little bit with this dataset. Probably it's the most popular one right now. So I'm sure there are persons and the categories. vehicles. And for the person category, you can see there are some people in front of the scene and some people that are far from the camera, and hence they appear very small. So in the same image, you have a strong variation, and the image on the right, probably this change is even more clear. So you have a very huge person. It's not a huge person, of course. It appears to be very large because it's close to the camera. But in the same image, you have a set of small people that appear far from the camera. And regressing bounding boxes or other shape representations that present such wide variation, it's not very trivial because the range of parameters in the network vary a lot, and there are some strategies to deal with that, such as anchors and other possibilities. There are some problems that are even tough for humans. So if you have a high density of objects, clutter in the background, it's very hard first to say how many instances are present, and let alone find the exact location of the objects. So in the image on the left here, I don't know, I can see 1, 2, 3, 4, maybe 5 elephants. And delimiting the boundaries is not trivial. There are occlusions, and it's very hard for a method to detect that different parts of the same object, they belong to the same particular instance or different ones. And the image on the right here is even tougher. I mean, you have lots of shapes. They are white, gray, and they are on very bright white background due to snow, and it's very hard even for us humans to count and annotate all these instances here. And these are not unrealistic image. On the contrary, they are present in the COCO dataset. Another challenge is that for some categories, you have a very strong and very large intra-class variation. So probably all of you can identify that all the images on the top, they relate to chairs, because you can recognize some semantic information, such as there is a seat, but visually they have very little resemblance in terms of shape, color, and so on. On the other hand, if you look at the images on the bottom, they all look similar to me. You know, they relate to different dog races, but I'm not an expert in dogs, so for me, they all look the same. And visually, they are much more similar than the chairs, but they belong to different categories. So for those of you who are interested in generic object detection, there is a very nice survey published at the International Journal of Computer Vision in 2020 that presents the challenges and the recent solutions. So this problem is highly related to my topic here. So what kind of representation is suitable to encode the shape of an object? So in the bottom here, I'm showing you some segmentation masks. They are not perfect, right? But they provide a rather accurate representation of the boundaries of the object and the interior. So you have giraffes here, you have dog, bike, people, plane, and several different objects present in the COCO dataset. And in the bottom, in the top, I show the horizontal bounding box, which is the default representation in red, and also oriented bounding boxes for encoding the same information, but in a different manner. It's not the same information, of course. The segmentation mask provides much more information than horizontal bounding boxes and oriented bounding boxes. As you can see, for some cases, the bounding boxes are okay. For some cases, such as the fork and the cake here, the horizontal bounding boxes are not good, but OBBs are okay, such as in the fork here. But for some shapes, such as the plane and the giraffe, neither representations are good because they comprise a lot of the background in the interior, and the default metric for evaluating object detectors is the intersection over union. And the intersection over union between the segmentation mask and these boxes here is clearly not large. And related to this choice for the object representation is how to regress a given representation, say horizontal bounding box, given an annotation. So you must define an error metric that relates to loss function that should be minimized during the training process. Now I'm going to talk a little bit about some existing solutions to, not exactly, there is not a one-to-one mapping between the challenges and the solutions, but some solutions to different modules related to deep learning object detectors. So there has been a lot of research, not only in the object detection problem, but image classification and several other segmentation and so on. So every year you see the introduction of 1, 2, 3, 4 new layers or new backbones, new combinations of layers for the problem of object detection. So probably VGG was the first kind of very deep network used in the context of classification and detection, then residual nets, dense nets, so on. Right now, there are efficient nets and attention modules. They all can be used to extract features. They can be combined in different matters, like using a pyramid of features, which is usually nice to detect different scale objects at different scales, such as the examples that I showed before. So in terms of the detection strategy, basically there are two main approaches. The first one is based on region proposals, which are evaluated. So these are two-stage methods. There is one stage for extracting the proposals, which can be done using an external module to the network or by a sub-module of the network. And probably popular examples are RCNN and the variants such as fast and faster. And probably the most popular trend right now is to use one-shot detectors. So at the same time, they detect the categories present in an image, and in the same pass, they regress the representation. In this example here, related to the single-shot detector, they used horizontal bounding boxes, and most of them, they use the idea of anchors, which are kind of predefined object shapes that are fine-tuned to get the particular instance, right? But there is also some strong research on anchor-free methods such as FCOS, and there is this kind of arms race between anchor and anchorless approaches. Another very crucial issue is how to explore data augmentation in a clever way. So usually, even if you have large data sets, you want to add more variability. So you can, if all your images are bright, you can synthetically turn them to darker images. You can change the color information. You can add geometric transformations. You can change the contrast. So there are several primitives that can be added and combined to generate new samples from existing ones. And how to define the set of primitives and the magnitude, the amount that you're gonna, the amount of deformation imposed by each primitive, it's a very, very hot research topic nowadays. So usually that augmentation is kind of orthogonal to the definition of the network, but not exactly. I mean, depending on for object detection in particular, depending on the choice for the object representation, you can use some primitives and not others, right? And for horizontal bounding box, you have strong limitations related to geometric transforms. So there is active research in terms of the choice for the object representation. Horizontal bounding boxes are, again, the most popular representations. Why? They are very easy to annotate. Usually you click on the top left and drag to the bottom right. So it doesn't take that much time. You don't have many parameters to regress. So you have 4 parameters to regress. But the codification is not good, particularly in applications for which you clearly have oriented objects. So there are several data sets, usually related to aerial images, where you have objects such as ships or trucks, as you can see here. And if you encode these objects as horizontal bounding boxes, you see that you're going to have several objects within the same bounding box. So it's very different. It's very hard to distinguish different objects using horizontal bounding boxes. So in the past years, we can see a rise in the number of approaches that explore oriented bounding boxes to codify the object shape. Of course, the network must be changed because you have to regress an additional parameter, the angular parameter. There are some details such as the parameterization of the oriented bounding boxes. You might not have unique representations, which impacts the training process, right? And this is an example of a recent state-of-the-art detector for oriented bounding boxes. And again, related to the choice of the object representation, it's the choice for the regression loss. So when you train a network, you have the annotation, the ground truth annotation, and you want your method to produce a parameterization, let's say a horizontal bounding box, that is close to the annotation. And most approaches, so the vast majority of approaches, they basically try to compare the corners of the annotated bounding boxes and the corners of the regressed bounding boxes. They have kind of the sum of L1, L2, or any other vector norm to define the regression loss. However, these strategies, they do not correlate directly with the intersection over union, which is basically the default metric for validating, right? So one possibility would be to use the IOU itself as a regression loss, which it's okay because it's differentiable for horizontal bounding boxes. But again, if the boxes, they do not present any intersection, the IOU is null and there is no gradient and the network cannot converge. So not until recently, like 2 years ago, the generalized intersection over union was proposed. The idea was very, very simple, very simple. Basically, there is an enclosing box to avoid these vanishing gradients, but other than that, it's roughly the intersection of a union plugged into the regression loss. And since then, you can see several methods proposing different variations, such as distance intersection over union, pixel intersection over union. And very recently, so I was aware of this work actually while I was developing my stuff here related to Gaussian distributions. So at ICML 2021, there was a paper that used Gaussian representations as intermediate codifications for objects. So now I'm going to talk a little bit about some alternatives that we have proposed in the past 2 or 3 years. Again, focusing on the representation of the objects and regression loss. So first, I'm going to talk a little bit about word planar regions. So this work was done with my former PhD student, Sergio Montazoli, mostly in the context of license plate detection. And there is an ECCV paper in 2018, and kind of extended version published this year. And the second part of the talk is going to focus on Gaussian bounding boxes. So we just have a preprint so far, but results are quite interesting. Of course, I'm biased to say that. But so in the first strategy, the idea was to encode the object shape as a warped planar region. More precisely, we used an affine warping. So the idea is that our object is going to be represented as a quadrilateral that can be obtained through an affine mapping of a canonical square. And the main idea of this representation in the context of deep learning is that you're going to learn the parameters of the affine transform. So you have a canonical square that is fixed, and then you learn the parameters that map this canonical square to the annotated quadrilateral. So our original motivation was to work with license plate detection. In this application, you have a planar region, which is a license plate. And when you have a perspective projection, such as in the pinhole camera model, you have a planar homography that maps the planar rectangular region of the license plate to the projected image. Basically, we approximate this homography as an affine transform because we have less parameters and we don't have the division in homography, so it was easier to converge. And we can see that the approximation was okay. And another advantage in this particular application, but in others as well, is that you can kind of undo the distortion caused by oblique views in perspective cameras. So you can warp back the license plate to a kind of frontal parallel view, and then in the full pipeline for license plate recognition, it's easier to recognize the characters. So I'm going to talk again about warp plane regions in the context of license plate detection, but the same concepts apply to, of course, any objects. So the idea to avoid handling pyramids of features or a variety of anchors, which we explored an off-the-shelf object detector or object detector that includes vehicles as a pre-processing stage. So in general, if you have an unconstrained capture, the license plate can appear very close to the camera or very far from the camera. But if it's attached to the vehicle, the relative size of the plate when compared to the vehicle is relatively fixed. So this is actually the kind of input that we are interested in. They can be extracted using any object detector that has the vehicles as a trained category. So we try different approaches here. This is not relevant, but the whole idea is that we want to detect the four corners of the license plate under a variety of transformations, and then we can warp these plates back so that we can perform OCR, right? So I'm not gonna focus on the vehicle detection part, neither on the OCR, but I'm gonna talk a little bit about the warp planar detection, which is actually the main contribution, right? So as I said before, this network aims to find objects that were affine transformed of a canonical square. Again, you can plug and play any backbone to develop your method. In these works, we have used ResNet blocks combined in a particular manner. They showed a very good compromise between running times and accuracy, and it's very easy. You can just replace it with more modern approaches, such as efficient nets, V1 or V2, or add attention layers, or so on. So the backbone is not a big issue here. The main question is how to define the classification and the localization heads. So for the classification head, you can use either a single parameter with a kind of softmax activation, since you have a single class, license plate, so you have the probability of having that object in a given location of the output tensor, and or you can have two neurons in a softmax manner in a competition way, so it's object versus not object. And the remaining 6 parameters are related to the affine transformation. So basically, this is the architecture that we used. Again, you can change it. You can use more modern modules or wherever. You can reduce, you can expand, depending on if you want to prioritize speed or accuracy, right? And in this example here, the detection head presents 2 channels in a competition-like way using softmax, and the affine parameters that are, they present a linear activation. So that's basically the idea. So you have an input image. So just as an illustration here, I show a cropped version of a vehicle. In the end, this is the final volume of the network. So the first 2 dimensions relate to the spatial resolution of the image. We have 4 pooling layers. So basically, the output volume is 16 times smaller than the input image. And you have 8 channels here, right? So if you look at the spatial resolution and consider it as an image, you have several cells. So the main goal is that you want some of these cells, at least one of these cells related to a license plate, should respond to that particular plate, right? And the remaining 8 channels, they should provide the parameters of the affine transformation. So that's the main idea. I mean, if this is the ideal activation of the classification part of the network, you're going to have a fuzzy activation here. You have an acceptance threshold score for pixels that present contiguous pixels that present activation. You apply non-maxima suppression. You have a single cell. For that particular cell, which is the most responsive to that object, you extract the 6 parameters related to the affine transform. You apply this affine transform to the canonical square, and then the corners of the canonical square are going to be mapped to the quadrilaterals that are annotated. And given that, you can, again, warp this quadrilateral to a frontal parallel view, which is easier to perform optical character recognition. I'm not getting into many details. I mean, I'm just going to provide you a brief overview of the math involved in this process, which is actually quite simple. So the idea is that you have a canonical square with a predefined size 2 times alpha, and this value alpha here is related to the training set. I mean, during training, you have a variety of sizes of the plates, and basically alpha is kind of the average size of the plates in the training set. So you have this quadrilateral, this canonical square. So this matrix Q contains the coordinates of these 4 corners, and the transformed version of the canonical square through an affine transform is given by this affine transform here. Just a very short comment about the diagonal of the matrix in the affine transform. This max between the V3 and V6, these 2 activation parameters here, is to avoid flipping and strong rotations, right? So we don't want to flip a license plate backwards. Moving to the loss function now, the classification laws basically must produce a probability value of having a license plate at a given spatial location of the final volume. So in the annotation, so let's say that here you have an annotated region, right, with a license plate, already redimensioned to the resolution of the final layer. You still have a quadrilateral, of course. Basically, you shrunk these quadrilaterals and you see how many cells fall inside this shrunken version of the quadrilateral. So basically, these pixels here, these cells here, are gonna be marked as related to this object, right? So you have in the annotation, you have an image with zeros and ones, and in our initial tests, we use the cross entropy as the classification loss. You can use different variations. You can use focal loss. We tried that, and results were quite similar, actually, but you can explore variants for the classification loss. So probably the most important part here is the regression loss, the localization loss that's going to guide the learning process of the affine transform parameters. So the whole idea is that you have an annotated plate, you shrink it to the final resolution of the network. Basically, you just resize it with a 1/16th factor based on the number of pooling layers that we have. And you get relative annotations centered at the cells that respond for that plate. So basically, that's it. You rescale the annotation and you shift it to the central location of the cell. So the idea is that you don't need to learn the absolute location of the central position, but just an offset with the starting point being the location of the cell. And the goal is to find the transformation for a given cell Mn that, when applied to the canonical square Q, matches the annotated and warped polygon quadrilateral P. So you have a set of four corners of the annotation and a set of four corners related to the warped canonical square, right? And for this work, we use the traditional approach that explores some kind of per corner loss function. So for each corner we compute, in this case, the L1 distance, right? You can use Huber or L2. Probably the difference is not going to be huge, but in this work, we use the L1 distance for each corner, and the final loss for a given quadrilateral is the sum of the individual loss of the four corners. And the final loss, as in most object detectors, so this equation here is basically used in most object detectors. So the idea is that for the last layer of the network, the final loss is the combination of the loss for each cell, and the loss for each cell comprises the classification loss, which produces a value typically between 0 and 1 and related to the probability of having an object at that location, and the regression loss. And this regression loss will only be triggered if there is an object present at that location. So in this case here, for this particular cell in the top, there is no plate related. So this guy here will not, affine parameters related to this cell here will not be used in the loss function. They will not be learned because there is no license plate to be detected. And there is a weight that balances these two losses here. So this is actually the prototypical loss function used in object detectors. So I said before that there was some coupling between the choice for the representation and the primitives. And this is the particular case for horizontal bounding boxes, oriented bounding boxes, and now warped planar regions. So the idea here is that if you have an HBB annotation, you cannot rotate the image, because if you rotate the image, rotating the horizontal bounding box does not lead a horizontal bounding box unless you have a 90 degrees rotation or multiple of 90 degrees. If you use oriented bounding box, yes, you can apply on the plane rotations. But if you use warped planar regions, you have a wide variety of geometric transformations that you can use. You can use any affine transform to the input image, and it still leads to a quadrilateral that is mapped through an affine transformation. So you have much more possibilities to explore data augmentation when you use warped planar regions. And that's what we have done for license plate detection. So we strongly use data augmentation. So basically, this is an example of many training images that can be produced from a single annotation. So on the top, you have an input image where you have the four corners manually annotated. There is a process of rectification. Basically, you apply planar homography that maps this to a kind of frontal view. You change the scale and apply random shifts. And then you rotate this image in 3D. You can apply off-the-plane rotations, because that's exactly the kind of scenario that you're going to encounter in real life. So if you have an oblique camera, your plate in the real world is going to be 3D rotated with respect to the camera, right? And you still have the four corners of the quadrilateral. And in the end, then you apply photometric augmentation, color changes, intensity, hue, and so on. So for these two papers, actually, we trained our model with hundreds of annotated images. I guess that in the largest set of annotated images was 400 images in the total, including cars, buses, trucks, and motorbikes. And just to show how well the method generalizes, we show here some results for the CPPD dataset. It's a huge dataset for Chinese license plates, so they have, I don't know, hundreds of or thousands of images. And in our process, we used 100 images from that dataset. And these are the results of our warped planar region object detector applied to some images in the CPPD dataset. I guess it's CCPD, sorry. So the ground truth annotation is shown in red, and our results are in green. And in my humble opinion, in some cases, our regression seems actually better than the annotation. So the annotation in that dataset, at least in the first version, I'm not sure if there is an updated annotation file, but in the original version of the data set, the annotation was kind of coarse, right? It did not correspond to the corners of the plate, right? So I'm going to show just a short video here with the full pipeline running. So the plates are detected with the warped planar region, and then for license plate recognition, we warp it back to the canonical view and then apply optical character recognition. So some comments about this idea of using warped planar regions. Of course, the good aspects are, first, you have a much richer representation than horizontal bounding boxes and also oriented bounding boxes, and you can explore several geometric primitives for data augmentation. And in that particular application, we used a relatively small training set. If you say that you use hundreds of images to train an object detector, probably people are going to say, oh, your method doesn't work or it overfits, right? But we showed in the papers results in several data sets, and it works surprisingly well. The bad part is that the annotation is kind of time consuming, right? But you don't have to annotate many images. And the loss function is one of those traditional loss function regression laws based on L1 or L2 distances. So a compromise solution is something that we started to work in the past year, and it's still going on, but results are quite promising already. So this is the same slide I showed you before, right? For some objects, you can see that there is a strong overlap between the red rectangles or the blue rectangles with the segmentation masks in the bottom. So how well is this overlap? So we performed a very simple test experiment running all the images in the COCO 2017 dataset, and we did exactly that. From the segmentation mask, we computed the HBB, the OBB, considered these objects as binary masks, and computed the intersection over union. As it's interesting to see that for some categories, such as airplane, shown in the previous slide, and giraffe, the intersection of your union between the HBB and OBB and the mask is quite low, right? For some other objects, it's also low, like fork, knife, and spoon. You see that for OBBs, it's a little bit better. And for some objects, they are quite good, like TV, microwave, oven. These objects, they are inherently rectangular in shape. So it's quite okay to use HBBs. So what are we proposing? We are proposing to use fuzzy representations for the objects. We are not going to use HBBs or OBBs. We are going to assume that the objects are represented as probability density functions, more precisely as 2D Gaussians, which we call Gaussian bounding boxes here, right? We can easily compute these Gaussian bounding boxes from traditional annotations such as HBBs, OBBs, or even segmentation masks. We also propose to map these GBBs to elliptical representations. And I think that the most important contribution is that we propose a probabilistic measure that relates to intersection over union, which is differentiable when GBBs are used and can be used to train object detectors. So basically, that's the core idea of a Gaussian bounding box. You have, as in a 2D Gaussian, you have the mean vector, and you have the covariance matrix, which is symmetric and positive definite, and it can be written in terms of the uncorrelated variances A prime and B prime, and the angle theta. So what's the advantage of this mapping here is that if you have an object detector that was devised to produce oriented bounding boxes, it probably produces the width, height of the OBB and the angle. So you can plug and play the idea of GBB with these OBB detectors, right? If you have a segmentation mask, then it's very simple to get the empirical mean and covariance matrix. Just apply the definition of the empirical mean and empirical covariance matrix. So in digital images, basically replace these integrals by summations. And when these regions are horizontal bounding boxes, you can find a closed form expression for these integrals here. So you have a mapping between the width and height of a given HBB to a covariance matrix. In this case, diagonal. If you have orientation, then you just rotate this covariance matrix in the idea of eigenvalues and eigenvectors. And again, just to be fair, this idea of two Gaussians, as I said before, it has been explored very recently by these authors here at ICML 2021. But our approach is considerably different in several aspects. So basically, this is the representation of the GBBs computed from the fork and airplane images in the previous slides. It's a fuzzy representation, right? It's shown here as a heat map, but there is no explicit boundary, right? But what happens if I want to get back a binary representation from a GBB? If you have Gaussian distributions, you have a strong relationship between the 2D distribution and elliptical regions, right? So there is a relationship between the 2D Gaussian, actually n-dimensional Gaussian, and chi-square distributions, which can be used to find the area of the distribution inside a given elliptical region. So basically, we can devise different strategies for obtaining an elliptical region from a Gaussian bounding box, right? Basically, you fix one value for R, and then you can get a binary elliptical region for a fuzzy region. So these are the binary elliptical regions extracted from the Gaussian bounding boxes in the previous slide, right? They are not bounding. I mean, they do not comprise the segmentation mask, but on the other hand, the intersection over union between these elliptical regions and the segmentation masks in the COCO dataset is considerably larger than the IOU computed for HBBs and OBBs, as shown in the previous slide. So basically, this is the same kind of box plot, but now adding also the elliptical regions computed with GBBs. So for stop sign, it's very large. Since it's kind of circular, it makes sense. Frisbee, clock, it's not that good for TVs and microwave, exactly for the same reasons that I said they were good for HBBs and OBBs. They are rectangular, and then, of course, rectangles are usually better than elliptical regions. But for most common objects, which is actually the goal of COCO, it's common objects in context, it seems that this elliptical representation seems to be better than HBBs or OBBs. So I'm moving to the final part of the presentation. And what's the proposed probabilistic intersection over union? So if you have probability density functions, you can compute the Bhattacharya coefficient, which basically provides an amount of overlap between these two distributions. So intuitively, it relates somehow to the intersection part of the intersection over union, right? And it provides a similarity metric. The Bhattacharya distance, which is related to the Bhattacharya coefficient through a log mapping, provides a dissimilarity metric. But the Bhattacharya distance is not actually a distance, right? It doesn't satisfy the triangle inequality. There is another statistical distance called the Hellinger distance. This guy satisfies the triangle inequality, and it relates to the Bhattacharya coefficient through this square root mapping here. The Hellinger distance provides values between 0 and 1. 0, it's a perfect match. 1 is a very bad match. So 1 minus Hellinger distance can be viewed as a probabilistic version of the intersection over union. When you use Gaussian distributions, you just plug the Gaussian distributions here, and you can find a closed form expression for the Bhattacharya distance, and then for the Bhattacharya coefficient, and then for the Hellinger distance. If you use the explicit terms for the mean and covariant matrix, you can find a differentiable expression in terms of all these parameters. This is very useful for devising a regression loss. So basically, we propose two different loss functions. One is exactly the Hellinger distance, which is 1 minus the probabilistic intersection over union. So this is probably the counterpart of generalized IOU. but using fuzzy representations and with Gaussian distributions. And it's interesting that when you use Gaussian distributions, since you have an infinite support, you don't need to worry about these representation not having overlap. They must have overlap, right? Any two Gaussians, they do present overlap. It might be very small. It might actually generate numerically a very small gradients. So we propose to use the Bhattacharya distance maybe in the beginning of the training process and then migrate to the probabilistic IOU. You can plug this strategy into any existing object detector that works with OBB or HBB. So if you have an HBB or OBB, we showed before in previous slides a mapping that can be used to obtain the GBB parameters for the annotation and for the output of the network. And then you can apply any of these two proposed loss functions. So this joint mapping here is fully differentiable. This pipeline is fully differentiable. So you can find the explicit derivatives of either HBB or OBB parameters in these probabilistic IOU-based loss functions. So this is an example. It's a simulated example of that mapping. So let's assume that blue is the ground truth and red is the initial box that you want to regress. If you apply direct gradient descent to L1, that's exactly what you have. So in the beginning, you can see that there is no overlap. So the intersection over union is 0, as it should be. But the probabilistic intersection union is not 0, right? So it tells the parameters where to go, right? And they smoothly converge to the final representation, right? So, of course, the Bhattacharya coefficient and the Hellinger distance, they do not map directly to the idea of intersection over union, right? But we did a simple experiment. So we produced several millions, actually, of horizontal bounding boxes, pairs of horizontal bounding boxes, computed the intersection over union, the typical intersection over union, computed the Hellinger distance and the probabilistic intersection over union, assuming a uniform PDF for these regions, and also the mapping to Gaussian distributions. And these are the plots. So when you use uniform PDFs, there is a very strong correlation between the intersection over union and prob IOU. When you use GBBs, there is some spreading because, of course, you add uncertainty due to the tail of the Gaussian, but still the correlation is very strong. So these are some results. Just plugging our L1 loss into two existing object detectors for HBBs, efficient DET and SSD, right? Compared with traditional smooth L1 and the IOU-based methods such as generalized IOU, distance, and center intersection over union. If you evaluate these methods using the intersection over union, our results are, they're still competitive, they're not the best. And actually, they're not expected to be the best because if you use the intersection over union to regress and to evaluate, if you minimize the intersection over union, you expect this approach to yield the highest intersection of union when you evaluate. On the same time, on the contrary, I mean, the parallel is the probabilistic IOU. If you use prob IOU to validate the results, then our method produces the best results, right? So a few examples here, visual results with the corresponding IOU and prob IOU. This table here shows a comparison with our approach for oriented object detection, right? So the data sets are quite different. So these two DOTA and HRSC 2016, which consist of mostly aerial images, they They provide OBB annotations, and there is a tool for computing several metrics per class and different average precision. And our results are very competitive. We have actually better results than those reported now. And these are some visual results. So I'm very close to completing 1 hour. I was planning to finish it in less than 1 hour, but well, here we go. Several challenges in object detection, and our contributions here were focused mostly on object representation and the definition of different regression loss functions. So for warp planar regions, it provides a rich description of the shape, right? For if you have a particular shape in the real world, which is deformed by a perspective transform, you can undo the perspective transform by computing the 4 points of the quadrilateral and then get a frontal parallel view, right? But on the other hand, you have some annotation, and it's not very easy to use more modern regression losses, such as those based on intersection over union. For Gaussian bounding boxes, basically you have a fuzzy representation. It allows the definition of a differentiable, probabilistic intersection of your union metric that can be directly plugged and played into any object detector. So some ongoing and future work for warp planar region, basically on applications here. You can, since you have the 4 quadrilaterals, you can explore these guys to perform pose estimation and then compute distances and speed of vehicles in video sequences. So these are the plots of the distances in time for each plate. It's roughly linear, which is expected since the speed of the vehicles and that small video is roughly constant. For GBBs, we believe that we can develop new detectors that don't need to go through OBBs or HBBs. So we can regress directly the parameters of the GBBs, which is the mean vector and the covariance matrix. There are some things to take into account because there are not any 3 values that form a covariance matrix. The matrix must be positive definite. So there is some interplay between these 2 variables. And this is one preliminary result that we obtain in the context of cell detection in microscopy images in collaboration with colleagues from the biology department. And in this network, we regress directly the GBB parameters. So sorry for going a little bit further from the time. Thank you very much. So these are the references. Probably if you look at the presentation, you can get into more details. And if you go into the papers, you're going to find the links to GitHub repositories where we have codes, full, total, or partial code. So thank you again, guys.
Thank you again, Cláudio, for the great talk. I thought a clever and elegant idea mixing geometric representations with a probabilistic view, and the results that you show are very solid. Now we're gonna start the round of questions. Remember, you can send the questions for YouTube chat and the Discord channel as well. And I'm not an expert in the field, but I have some curiosities.
Okay.
I was wondering what happens with GBB when it faces very thin, elongate objects.
Yeah.
Does it compromise the convergence?
Yeah. The problem is not exactly thin objects, but very small objects, because the variances are small, and since they appear, if you compute the derivatives, then you have an inversely proportional parameter to these guys. That's a very good point. So usually you have to apply some gradient clipping to avoid these kind of issues here. But that's one of the drawbacks, one of the limitations of the approach. If you have thin or small, I mean, if one of the dimensions is small, then you might have some issues in the gradient. But if you clip them, it still works.
And another curiosity is, is it possible to use an adaptive representation for the objects? I mean, breaking the object in multiple GBBs in order to build a Gaussian mixture model. It's making sense.
I think it does. The problem is that, so the main advantage of using Gaussian distributions is that you can find a closed form expression for the Bhattacharya distance and all the other distances used in this work. As far as I know, there is no closed expression to compare two mixtures.
Okay.
There are other alternatives, like there are some, so there are other 2D distributions for which you can compare closed form expressions for these Bhattacharya distance and coefficient. And this might be a possibility, not stick to GBBs, but maybe use other parametric representations that allow these closed form expressions here.
Okay. And the last question is, did you try to use another distance between probability distributions in GBBs, for instance, Kullback-Leibler divergence?
So actually, when I talked about the related work that used GBBs, those guys in the ICML 2021 paper, they use the Gauss-Wasserstein distance, right? But the problem is that it boils down to kind of L1 or L2 distance between when you restrict the problem to horizontal bounding boxes, the GWD, it boils down to the L2 distance between the center and width and height of the HPB, which actually it goes on the other direction of using intersection over union to guide the regression loss. Okay. These same authors, they recently provided a regression loss based on Kullback-Leibler. But the problem is that it does not relate directly to the intersection over union. You need to find an additional mapping function to with other hyperparameters to use them as a regression loss.
Okay.
Right? So it's again, yes, you can, but as far as we know, this is the only one that maps really to the intersection over union.
Okay. And now we would start with the questions with the audience. The first question comes from Discord channel by Telmo Jr.,
Yep.
EF Sul. Which convolutional implementations are suitable for detecting objects with wide variation in size? Example, plant disease.
Actually, this is not exactly related to the contributions in this talk, but actually most of them, most methods that you can find code in the internet, in the official repositories, they do handle wide variety of objects. So if you go to efficient.dat, yes, there is a pyramid of features and there is the idea of anchors. Even SSD, by the use of anchors, you can, even if the original implementation does not provide the range of scales that you need, you just change the set of anchors and then they have support for that. So basically the short answer is basically any, right?
Okay.
Recent.
Next one comes from Davi Menotti. He asks, on the final slides, is camera calibration required for vehicle speed estimation?
So you need to have the intrinsics, right? You have to pre-calibrate the camera, which is, well, in theory, you have to do it only once. But once you calibrate it, then it's all done. But yes, you need the intrinsic parameters to estimate the speed.
We have over time, we don't have more questions, but I want to thank you, Cláudio, again. Thanks the audience for the questions. You can talk with Cláudio in the Discord channel, and stay tuned for next technical session regarding image and video analysis. See you later.
Okay, thank you all. Go to the technical sessions. They are very interesting. Bye-bye.
Bye.